Hi everyone, this is Manas, your friend and tutor, and guys, today's session is going to be super awesome. This is our example number 3 in the series of videos on bending of beams from the subject, rather the beautiful subject, mechanics of solids, strength of materials, whatever you may call it. Some people also call it mechanics of materials. Okay, so what we've got to do in today's session is that we need to find the maximum bending stress in this cross section. So what we've been given is all of these diagrams are part of the problem. Okay, listen to this very carefully. This is the front view and this is the side view. Okay, now you can clearly see that this load is acting at a certain angle. We can actually calculate that angle, and we can also resolve this load into the corresponding x and y components. That can be done very easily. But what we are basically interested in is, first of all, finding the bending moment in this cross section. Why? The reason being very simple. What are we supposed to calculate? Is the maximum bending stress. Just take a look. So what are the inputs, what are the ingredients that are needed to find the maximum bending stress? Well, they are in the form of bending moment, where bending moment at a distance of 1 meter from this fixed end. It is exactly at that point, it is exactly at that cross section, 1 meter, right? So this is just a supplement to exactly show you how the real beam would look. If you take a look at this from the front, that's the front view. If you take a look at it from the side, that is the scaled up side view. You can say this. Okay. So it is at this cross section we are interested in, first of all, finding the bending moment, and it is with that bending moment, when you plug it in over here, you will get the value of maximum bending stress. Okay. So how to approach? Again, tip number 1, whenever you come across any bending moment of beam problem, try to work out the location of neutral axis. And by the way, the neutral axis is your centroidal axis. You know this. If you haven't seen my lecture number 1 on bending of beam, go ahead and watch it. Well, the link can be seen, can be accessed from the description. Okay. All right. So time to begin. Location of the neutral axis. Once you get the location of neutral axis, you will realize what this is. What is C? C is nothing but the farthest fibers. Yeah, what you can also write is distance of farthest fiber. C is nothing but the distance of farthest fiber from the neutral axis. So once you know where the neutral axis is situated, you'll get to know where the farthest fiber is, and it is at that fiber you're going to get the value of maximum bending stress. And again, well, this is very trivial. This is very fundamental. Moment of inertia calculating, not moment of inertia, but the area moment of inertia, to be very precise. Always remember, in the environment of bending of beams, we'll always be working out the area moment of inertia and not the mass moment of inertia, right? Okay, let's begin. As I said, tip number 1, always start with the position of neutral axis, then try to find the moment of inertia of this cross section, and then you can get going. Okay, everything will follow, right? Let's begin. All right, so this is what we have. This is how the beam would look from the side. Let's say this is 1, then let's say this is 2, let's say this is portion 3 of the beam. So beam has been made with respect to 3 rectangles. You can say this. If you just take a look at this rectangle, that's 15 and that's 200. So it is going to obviously have a centroid, its own centroid somewhere here. Let's call this centroid C1. Similarly, this small rectangle over here, how much? 250 by 20 will have its centroid somewhere here. Let's call this by C2. And in the same fashion, this is 15 by 200, very identical, and it is going to have its own centroid somewhere here. Let's call this as C3. That's very basic. What we are interested in? Well, it is all about these values, areas, and the corresponding distances of C1, C2 and C3 with respect to a particular benchmark. Let me tell you. Well, you need to do calculations. You need to take the distances in the form of y1, y2 and y3. You need to select a reference point. Guys, you take this as your reference point. Let's say this is your x-axis. Let's say this is your y-axis. Let us keep it very simple. At the bottom left corner, we have chosen our origin. Now, one thing is very clear. It is symmetrical with respect to a vertical axis. Okay. So it is symmetrical with respect to a point that is at a distance of, let's say 125 from here or 125 from here. You can also say Rather, you can argue, so it can also be said that that point, right, about which you are drawing the vertical line is at a distance of 125 plus 15, that is 140, if I'm not wrong, 140 from here or here. Yeah, that's perfect. That means you already know the location of this vertical line. It is symmetrical, right? So at the center, you can make a vertical line. That's quite simple, but we are not interested in that vertical line. What we are interested in is this centroidal X. We are not interested in centroidal Y. Okay, that is very much evident. Now, first of all, let us try to work out the areas. So area 1 is going to be equal to this 15 multiplied by this. How much is this? 200 multiplied by 15. 15 2 is 30. So this is going to be 3000 millimeter square. Brilliant. What about area 2? Area 2, 250 multiplied by 20. 25 2 is 50 and double zeros. 50 and double zero. This is going to be m square. Again, this is area 3. Well, area 1 and area 3, they are identical. So again, 200 multiplied by 15 will return the same value, 3000 square. So that was all about areas. Now let us find the distances of the individual centroids of those three rectangles, okay, with respect to this, with respect to the x-axis, this distance y1, this distance y2, and this distance y3. So y1, this is 200, half of 200 is, well, 100. So y1 is going to be 100 mm. Let me just write this up. Y1 is going to be equal to 100 mm. Keep watching. Y2. What about y2? If you just take a look, if I can just draw a line like this, how much is this distance? Let me put it up this way. How much is this distance? So this entirely is 200. This is 10 millimeters below, isn't it? This is how much do we have? This is 20. So half of 20 would be 10, isn't it? This much is 10. So this is 200. 200 minus 10 will give you this value. That is going to be 190. Brilliant. So y2 works out as 190 millimeters, and again y3 is going to be identical as y1. That's 200. Half of 200 is going to be 100 millimeters. So guys, when you try to plug in all of these values into this formula to work out the centroid, what you have is the position of neutral axis, and that is going to work out as 140.9090. So let me round it off to 2 decimal places, and that is going to be 140.91. Here we go, 140.91. 140.91 millimeters. Now you can also fix that up over there. Okay, that can be done, and let's do that. Why wait? Let me fix it. Okay. So the neutral axis lies at a distance of 140.91 from the base. This is the baseline, right? From 140.91. NA. Let me write this as NA. Simply NA. Neutral axis. That's the neutral axis, and it is at a distance of 140.91. Well, everything is in millimeters. I'm not writing the units, so you can manage. Okay, everything is in millimeters. You can also work out from the bottom. This is 140.91. So if you just subtract 140.91 from 200, you're going to get the corresponding value from above. Okay, so this is exactly what I'm saying. So 140.91, how much is this going to be? 200 minus 140.91. This is, well, 59.09. 59.09. So we know exactly where neutral axis is. Here from the base, here from the top. What is C? Distance of farthest fiber from neutral axis. If you see, there is this cantilever over here. Let me draw this figure, a rough figure, and this is when it is loaded. Obviously, it is going to bend somewhere in this fashion. So you are going to have this neutral plane, isn't it? That's the neutral plane. So the portion of the beam below the neutral plane will be undergoing compression, and the portion of the beam above this neutral plane will be undergoing tension. Similarly, if you take a look at this from the side view, in the side view also, the portion of the beam above this neutral axis, this much portion, this portion will be undergoing tension. All the fibers are being extended, whereas the portion of the beam below the neutral axis is going to undergo compression, which essentially means if you go here, for all positive values of y, you are going to get a positive value of stress, and for all negative values of y, you are going to get all negative values of stress. All positive values of stress represents that the fibers are under tension. All negative values of stress represents that the fibers are going to undergo compression. Why? You can see this. Everything below this neutral plane, okay, is undergoing compression, and everything above the neutral plane is undergoing tension. That is the idea, and I think I should move away and you guys can note these things down. Pause the video and note it down. Okay, moving ahead. So we know exactly the location of neutral axis, and this, by the way, this fiber over here, this is the neutral axis, and this fiber over here, there are going to be fibers right here, isn't it? Fibers, everything, all the fibers. So all the fibers which happen to be at a distance of 140.91, right, they are going to undergo maximum bending stress, right? So you know the value of C is 140.91. Now this is known to us. Okay, you don't have to worry about C anymore. That C has been conquered, 140.91, done and dusted. Now you need to focus on what the value of neutral axis, what the value of moment of inertia with respect to the neutral axis is going to be. Okay, now this is a brilliant formula. Okay, I have framed it based on my convenience. So how to proceed? You want to find the moment of inertia of this cross section with respect to the neutral axis. So you need to find the moment of inertia of this rectangle 1 with respect to the neutral axis, then rectangle 2 again with respect to the neutral axis, and then for 3 also. That is why I have split it up into 3 different area moment of inertias, right? And all of them have to be individually worked out with respect to this axis, that is the neutral axis, and let's see how can that be worked out. Here is the formula. Let me just try to frame INA1 for you. INA1, where shall I do this? INA1 is equal to, remember, if it's a rectangle, that's B, that's D. Okay, so this is XX. I with respect to its own centroidal axis is equal to B D cube by 12. Remember this, right? Okay, so I with respect to any axis, with respect to neutral axis, with respect to its neutral axis, okay, is equal to I with respect to its own centroidal axis. So we are talking about rectangle 1, its own centroidal axis is at C1. So if I draw a line here, then with respect to that axis, its moment of inertia, only this much portion, is going to be BD cube by 12, that is 15 into 200 cube divided by 12, and here we go, 15 into 200 cube divided by 12, done, plus the area of rectangle 1, that is 3000, lovely, that is 3000, what else, multiplied by what? Okay, just take a look at this, distance between the axis. What axis? So you see, we have an axis right here, right? Now this distance happens to be 100 and this is 140. Just take a look at this. We want the distance between the two axes, distance between the neutral axis and this axis, centroidal axis of this rectangle 1 only. That is 140.91, this is 100. Okay, let me write this, it is better to write. That is 100 for you. So the distance between these two axes is how much? 140 minus 100, 140.91 minus 100, and the square 140.91 minus 100, and just square it up, right? You are going to get a certain value. And by the way, the same analysis will be done for this rectangle also, right? Everything will be same, 15 into 200 cube divided by 12, and then plus area is going to be same, it's identical. So this, by the way, this INA is also equal to INA3. So let me just write the final value. INA1 is equal to INA3 is equal to, and finally what's going to work out is this Okay, that is 15.02 into 10 raised to 6. 15.02 millimeter raised to 4. Done. Now let us try to work out the moment of inertia, area moment of inertia of this rectangle 2 with respect to this neutral axis. Okay, so I Na2 will be equal to, just take a look at this rectangle. The moment of inertia of this rectangle with respect to its own centroidal axis, B d cube, 250, 20 cube. 250 into 20 cube divided by 12 plus the area. What's the area? 5000. Okay. 5000 multiplied by, again, distance between the axis. This is the axis of the rectangle 2 and this is the main axis. What is the distance? Now this happens to be at a distance of, this is nothing but y2 from here to here. This is how much? Y2 is 190. So that's 190 minus this 140.91 and done. 190 minus 140.91 and square it up. Okay, and what you are going to get is the final value of the moment of inertia of rectangle 2 with respect to the neutral axis, and that's equal to, let me check, 12.21 into 10 raised to 6. Okay, 12.21 into 10 raised to 6 millimeter raised to 4. So you've got all the values, INA1, INA3, INA2. Plug it in into this. Well, these two are same, so it's going to double. 30 plus 12, 42. So the approximate value that you are going to get is 42. Let me get the exact value, and this is, where is it gone? 42.25 into 10 raised to 6. 42.25 into 10 raised to 6. Final value is this, 42.25 millimeter raised to 4. Okay, and that's a brilliant result, because now this also has been conquered. Let me mark a tick. This also has been conquered, that is 140.91. This is 42 point, how much? 42.25 into 10 raised to 6. What now needs to be done is that we want the bending moment at a distance of 1 meter from here, from the fixed head. Okay, how to calculate that? So guys, now let us proceed with bending moment calculation at a distance of 1 meter from the fixed end. Okay, this is going to be super awesome. So just keep watching, and here we go. So let me make a rather bigger figure. Right? You know how it looks from the side? Something like that. Right. And we have, what else? We have a load over here, right here. Okay, now let us not make this, let us rather resolve it into components. If you watch carefully, let me just do this very quickly. In order to get the moment, you need to resolve this into components. Only this much portion of the beam has been remade over here. So basically what happens, guys, that's 2.6. okay, forget about the units, it is kilonewton, we'll recall it. And if this is theta, then this component over here is going to be 2.6 cosine theta, and this component over here is going to be 2.6 sine theta. Now if you watch carefully, this is theta, okay, and you can actually work out cos theta. Cos theta is going to be equal to base by hypotenuse, that is 5 by 13, and sine theta, if you watch carefully, sine theta is going to be 12 by 13, perpendicular over hypotenuse, that is 12 by 13. You just need to plug in these two values. So instead of, just take a look, sine theta 12 by 13. So 2.6 multiplied by 12 by 13. 13 times of 2 is 26. So 0.2 is going to be this much, 2.6. So 12 multiplied by 2 is 24. 0.2 is going to be 2.4. So that's 2.4 kilonewtons for you. And what is the component? This is the vertical component in the downward direction. Okay, brilliant. How much is this? 2.4 kilonewton. You'll understand why I've made it this big. You'll understand this very soon. Secondly, what we have is this. So that's done. That's done for you. 2.6 cosine theta, 2.6 into cos theta. Cos theta is, you know this, 5 by 13. So 13 times of 0.2 is 2.6 and 5 times of 2 is 10. So 5.2 is going to be 1.0 or simply 1 kilonewtons. Done. That is 1 kilonewton. So that's 1 kilonewton for you. So these are the two forces acting at this point. Okay. And anything else? Well, we are good to go now. And it is at this cross section. Let me make it once again. It is at this cross section. So according to the question, this has been marked as AA, and this happens to be at a distance of 2 meters from the free end, and also happens to be at a distance of 1 meter from the fixed end. Done. Question is set up now. It's very clear. You need to find the bending moment at this spot. Once you get the bending moment, plug it into this equation and you're going to get the maximum bending stress. And you know very well, the maximum bending stress is going to happen in this region. In this case, it's a cantilever beam. Okay. Once again, the beam would bend in this fashion, isn't it? The beam would be bending in this fashion. So this is the neutral plane. This is the neutral plane. All the fibers below this neutral plane, all the fibers below the neutral plane are going to undergo compression. All the fibers above the neutral plane, are going to undergo tension. So obviously the maximum bending stress which we are going to get is at a point which is at exactly at this point, which is actually below the neutral axis, and therefore the maximum bending stress is going to happen in compression. That's quite true. Bending moment about at this cross section. So let's focus on only this much portion of the beam, and basically we also have the neutral axis. Neutral axis is actually part of a neutral plane. You can make the neutral plane somewhere here, and this this exactly is this much, 59.09. Remember, this is in millimeters. So while plugging in the values, we need to plug it in meters, and this much is 141.91. Okay, fair enough. You add them up, you're going to get this depth, that is 200. Okay, so you want the bending moment at this cross section. This way. Okay, focus on only this much portion of the beam. We want the bending moment here. A, and if you just take a look, this is 2.4 kN and this is 1 kN. Okay, these distances are known to us. That is 59.09. This is 141.91. What we want is the bending moment with respect to this point. About the neutral axis, we want the bending moment right here. M at AA is equal to, so just take a look at this, 2.4. It is this force with respect to this point. What is the nature? Going downwards, it will try to bend the beam in this fashion. What is this? A clear-cut case of hogging. That means a negative sign minus 2.4 multiplied by. So this is the force. This is the perpendicular distance. How much is this distance? That's 2 meters multiplied by 2 and done. Also take a look at this force. 1 kilonewton. Again, this way. It will also try to bend the beam in the hogging fashion. Negative sign 1 multiplied by this 1. Extend this. Okay. This is force multiplied by this perpendicular distance. Force multiplied by this perpendicular distance, that is 59.09. Well, by the way, this is in millimeters. So if you do the conversion, 0.059, this is going to be in meters. So you just need to find this value of bending moment at section AA, and this is going to precisely work out as negative of what? I've got the value already. Kilonewton, and this has been converted to meters, and this is also meters. So kilonewton meter. So the answer is 4.859. 4.859 kilonewton meter. Negative sign just indicates a case of hogging bending moment. That's it, nothing else. Negative sign is just an indication that the bending moment is negative in nature, and rather the beam would bend. It's in something like this. If this value had worked out with the positive sign, then the bending moment would be in this fashion, right? This is a clear-cut case of sagging. The bending moment is negative this way, that is hogging. That's it. Okay, so that's done. So you just need to plug it in. Okay, now we really are not interested in this negative sign. We just need the absolute value. What we need is the absolute value of BM. That is exactly what we are interested in, right? If you just take a look at this, let's say you've got a beam like this. That's a fixed at one end, free at the other. That's a cantilever beam. If you try to make the bending moment diagram, that bending moment diagram would have the maximum bending moment over here and zero bending moment at the free end. You try to make a plot, it would be something like this. What I am trying to essentially stress upon is this is the zero line or the baseline. All the value of bending moment that you are going to get at different points. Once you start from the fixed end and you move towards the free end, the values are going to decrease, or rather I should say that all the values are going to be negative. Okay, so don't worry. This is exactly the reason why you've got this negative sign over here. Okay, what we are basically interested in is the magnitude of bending moment at this cross section, which we are going to plug in over here to find the maximum bending stress, and well, everything will be over then. Okay, here we go. Maximum bending moment, not the maximum bending moment, but the bending moment at this cross section. The bending stress is going to vary, okay, from the neutral axis. If you move upwards, it is going to increase, and if you move downwards, it is again going to increase, right? Above is the region of tension, below is the region of compression. You know that, okay? This region, let me write this once again. This region, all the fibers are going to bend like this, right? Like this, like this. So anything below this neutral plane is going to be under compression. This is the region of compression. Anything above the neutral axis is a region of tension, and that is true. Okay. So let's do this. Almost. Sigma max, final touches, sigma max is equal to M, the value of M. This is in kilo Newton meter. Okay. We are interested in taking the absolute value, so neglect the negative sign. 4.859. 4.859. Convert the kilo. How much is kilo? 10 raised to 3. 10 raised to 3. Okay. From meter, convert this in millimeters. We are going to work out everything in newtons and millimeters so that the final stress value obtained will be in Newton per mm square, right? Which is easily convertible in megapascals. I'll tell you that. Remember, everything that we are plugging in is in newtons and millimeters. Remember this. So this now has converted into Newton meter, and if I also multiply 10 raised to 3 one more time, this is now kilo, not kilo, but this is now converted to Newton mm. Done. Okay, so that's done. M is over. What about C? What about C? How much is the value of C? That's the value of C, 140.91. So it's already in millimeters, so this is going to be 140.91. Done. All of this divided by INA. I got the value of I, 42.25. This is already in millimeters, so there is absolutely no point of converting. 42.25, 42.25 into 10 raised to 6. Again, this is Newton mm. Okay, this is mm. This is m raised to 4. Just try to play with the units. You are going to get Newton per mm square as the unit for the maximum bending stress. And what is this value? First of all, let me just make a quick check. Where is it? 4.859 10 raised to 6, 140.91, 42.25 into 10 raised to 6. That's also millimeters power 4. Yeah, done. Once you plug it in, what you are going to get is this 16. Let me just try to do this in a calculator. Okay, 4.859 into 10 raised to 6 10 raised to 6 into 140.91, okay, divided by 42.25 into 10 raised to 6 and close the bracket. This is what you get, 16.2. Is this visible? 16.2, 054, whatever. 16.2 Newton per millimeter square. Now remember a conversion, and this is going to be super awesome and super helpful. 1 Newton per mm square. 1 Newton per mm square. What is m? M is nothing but milli. What is milli? It is nothing but 10 raised to minus 3. So what is this? 1 Newton per 10 raised to minus 3 and meter and its square. That's equal to 1 Newton divided by square of 10 raised to minus 3, that is 10 raised to minus 6 meter square. What is this? 1 Newton, not just 1 Newton, not 10 raised to minus 6 shifts upwards, 10 raised to 6 Newton per meter square. You can also write this as 1 multiplied by. And what is this fellow? This is a very big fellow. It's mega. Mega is written as capital M. So what you get is 1 mega. And what is this? Newton standing above a square tile of 1 meter square is Pascal. Remember this. Mega Pascal. So by the way, 1 Newton per mm square is 1 megapascal. You can essentially write this as 16.2 megapascals. That is your final answer. Right? Okay. Please note these things down. Let me tell you something else. Pause the video. Okay. Before noting, pause the video. Okay. I'm sure that it is done. Now what? Just think about this. At this cross section, at this very cross section, if I can rub this off, what are we calculating? We know what the bending moment is. So the bending moment, let's say it's in this manner, right? So there are two kinds of forces which are acting, two external forces. One is this, because of which there is going to be some kind of shear force also. Let me put it up this way. So this is the bending moment, A. There is going to be some shear force in this cross section, isn't it? Let's call this as V. There is going to be, if this 1 Newton is acting over here, then at this cross section, there has got to be a horizontal force acting in this fashion. Now guys, what we have calculated, this 16.2 megapascal, is purely because of this MAA ma. Okay, that is bending moment at this cross section, AA, right? Bending stress because of this bending moment. Rather, if you in the upcoming session, I'll also let you know how to work out the stresses because of the shear force. That is something that we are going to take up in shear stresses in beams. Again, a very interesting concept. And you can actually calculate the stress over here. You can actually calculate the stress because of the shear force, the stress because of this normal horizontal force, normal to this cross section. And then you can superimpose all of them to find the total or the net stress at this cross section. One because of bending, one because of shear, one because of this normal horizontal component of force, right? All of these things can be done. So that will come up later on in the upcoming sessions. So yes guys, that was it for today's session. I'm going to see you again with final example number, this was 3, example number 4, and that will be the final example, after which we'll close the bending of beam chapter, right? And then we're going to begin with a new chapter. So yes, that was it for today. I'm going to see you again in the next video. Until then, take care, have a nice day, keep learning, keep watching. Thank you.